Ezra Hoch, and I'm the Chief Architect at Elastifile. And I'd like to go over some more details in the architecture. Just before we start, I want to answer the question about how exactly we're deployed. So in the hyperconverged mode, let's say this is an ESX, will be some VM here running, Elastifile, and then there are the different user VMs, and they'll just connect to us through some IP we expose, and they see us as just an external storage. And if we have another ESX, and again we're running here, and the VMs connect to us, the IP we're using here and here is the same IP because it's exposed only locally, which means that if this VM would move over here, it will just continue connecting to us. And this is kind of what we see as a cluster. We see the clients as connecting to us externally. When we're in the dedicated storage mode, then we'll just be the entire machines, and we'll have multiple connections. We expose this as virtual IPs exposed externally, and then you can connect to us whatever way you want. Okay, so I hope this
Okay, so if I'm running dedicated storage nodes and hosts that are not running Elastifile.
Yes, we don't count them as nodes.
So getting back to the counting as nodes, we have nodes that we have systems that run Elastifile that have local storage. That gets added to the pool. That's clearly a node.
Yes.
We have nodes that access that storage via SMB and NFS. That's clearly not a node.
Exactly.
Yes.
Now, in between, we have nodes with the client software that you mentioned. So let's talk about the client software and what it actually does relative to the standard protocols and whether those count as nodes or not.
So they count as nodes, and that's a very good question, which I'm going to talk 30 minutes about. Okay.
I told you to that.
Start the clock.
Talk 29 minutes, you're in trouble.
Okay.
I run a lab, I got to stop.
So what I'm going to go through is an overview of the data path, how we handle metadata, specifically scaling of metadata, and clustering. And the reason I'm going to concentrate on these is because these are kind of like the base components of our architecture, and all of the advanced features kind of derive from these. So that's why I'm going to concentrate on these specific aspects. Okay, so when we started designing the architecture, we had a few goals that we wanted to reach. So we wanted to be an enterprise-grade file system, which means we need to support POSIX semantics and advanced data services, snapshot, SNDR, and so on. We wanted to have consistent high performance and low latency. In our case, we wanted to have the data path to be predictable, so we don't want to have different IOs having large variance in the number of actual disk IOs they do, and not to have any sort of data caching. And we wanted all of this to be in a mode that is cloud ready, so that means both scalable data and scalable metadata, and to work well in noisy environments. So because you run in the cloud, you're sharing the infrastructure with other workloads, and they affect the kind of service you're getting from the infrastructure. And we incorporated different mechanisms in order to be able to respond quickly to these kind of changes. As Shachar mentioned, heterogeneous hardware, so it's hard to have it scale to have the same hardware. So you're going to have different SSD types and different node types. And the access patterns of the workload vary. Now, these specific 2 points are what caused us to, motivated us to develop a very dynamic data path, which I'm going to go over in a second, where we can not only choose where each piece of data resides, it can be chosen at the time of the I/O to which disks it's going to go to, but we can actually even cancel that I/O and re-choose to a different location where it's going to be persisted. So this allows us to handle all kinds of short-term fluctuations. Okay, so internally we manage objects. Both data and metadata are presented as variable length objects. These objects are used to construct files and directories. I'll show you in a minute how.
There was an item on the prior slide about no data caching.
Yes.
You don't have any data caching? In
No. Zero. Only metadata.
Not for reads?
Nothing.
don't believe in that in Flash.
You don't believe in data caching?
Caching?
No, no, not like they don't believe it does. It exists.
No, it's not exist. It doesn't exist. And in NVMe, specifically, if you have NVMe, it's pointless. Really pointless. You're wasting memory. Really.
If you have the memory, we'd rather use it for metadata caching. It will give you more performance.
You support metadata caching?
Yes.
Yes.
We do caching for the metadata. It makes sense for all kinds of reasons. You can see it.
We're going to have to talk offline.
Glad to.
Okay, and this is an important point about how we handle metadata. So each object can be owned by a different node. And this ownership is dynamic and fine-grained. So dynamic means it can change over time, and fine-grained means that we can do it on a per file or directory basis.
And an object,
So we're going to see, those are the objects, okay? So a file encoding or layout is composed out of 3 types of objects: a file metadata, file mapping, and the data objects. The file metadata is pretty simple. It's the A time, C time, M time, different permission bits, and so on. A file mapping object maps half a megabyte of address space. And the way it maps it is it has 128 entries. Each one points to a 4K data object. And then the data object, the reason I'm mentioning that they're variable size is because we support compression by default, so these can be anywhere from 1 byte to 4K. So this is how our file layout looks like. So a file of 10 megabytes will have 20 file mappings. And they can point to any data objects. We'll see later how this kind of mapping allows us to be very dynamic in our data path. Sorry. Our directory layout. So again, we have a directory MD, which is very similar to the file MD object. And then we have what we call dir listings, which are basically a list of file names and pointers to either file or directory. We call those OID, object identifiers. And they're sorted by some hash in order to be efficient for lookups. And the way that the structure itself, when you have large directories and you have multiple directory listings, is based on an extendable hash table.
Are you using any special technique to keep that? Because that sounds like that hash table is the most important thing in this whole architecture. Without that, if that gets corrupted in any way, you can be in trouble, right?
So all of our metadata is replicated. That's our replication mechanism. So according to the number of failures you want to support, either 2 or 3-way. And we have CRC in order to detect if one of the copies was corrupted.
Is there any consistency methodology you're using for the hash table?
I'm not sure I follow your question.
To make sure that that it is what it's supposed to be at a given time?
So every change to it occurs transactionally. So it stays consistent just by the fact that every change to it is transactional. Okay, and this is first.
It's that process, I guess I'm looking for a little insight on it, how you're making that transaction happen.
Okay, so we can talk about that a little bit later. We need to have some more, to know a little bit more about the system before I can answer that. Okay. So let's look at the main components we have. So we have the protocols layer, which terminates the different protocols, NFS, SMB objects, translate them into internal semantics. So in the case, for example, it will, in this setting, the protocols there will be kind of like here, terminating whatever is coming in. The second layer is the metadata layer, which basically does the actual file system work, including distributed transactions and all the consistency guarantees. And then the third layer is the persistency data layer, which is in charge of persisting the journal for the transactions. And its high availability is via n-way redundancy. Now, what's important to note is that we have 2 layers of mappings. So you've seen the first layer, which is the file system level layer of mapping. And then we have another object level layer of mapping, which allows us to leave all of the complex file system operations for snapshots and for AsyncDR and for just maintaining consistency of file system at the level of the metadata. And all of the complexity of rebuild and rebalance, which is more interesting for the data store, does that using the object level mapping. Okay, so we have, I'm not going to talk too much about the object level mapping. I'm just saying that it exists in order to explain why we can do rebuild and rebalance without needing to change anything at the file level system. Okay, because the file level talks in objects, and that's all it cares about, and then the data layer understands this object language, but puts the data wherever it wants according to its considerations. So we can just rebalance, and all of the other higher level features don't care about it. Let's go and see an example of data path. The way we do redundancy and at all the model that we assume. So we have n-wave replication for our data, also for our metadata. Persistency is always before we acknowledge the user. So if we're a two-way replication, we will always have the data and the changes to the metadata persisted in two locations before we acknowledge the user. We do not assume a write cache. We do not assume NVRAM. If we have NVRAM, we can use it in order to improve the wearing of the devices, but it's not a requirement. And of course, everything is complete power failure resistant at any stage of the operations. The system can choose wherever it wants to write any I/O. So we have a distributed write anywhere semantics. We'll see that in a minute. And it's important to see that, or to notice that the metadata path and the data path are completely separate. This allows us to improve the performance of the data because we send the data over the network once and not twice. And it also allows us for the metadata to be very dynamic. So we'll see that also. Our consistency is achieved by a distributed transaction layer. The metadata is journaled. Every change of the metadata is journaled together with the operation that is actually happening. And it can be journaled anywhere in the cluster. Again, this is important in order to be able to mitigate fast occurring fluctuations. And it's persisted in a distributed journal, which it's not a fixed size where every specific operation needs to go to some location, but it can be anywhere. And one point about our failure detection, we're not assuming any special hardware. When we do fencing, we are not fencing using power or network capabilities. It's all in software, assuming regular network communications. So let's see an example. We have a piece of data coming in into our protocols layer. This is where we compress the data, compute a hash for dedupe if it's on our data container on a file system. And this is also where user-defined policies can be determined. So for example, if we see that this is a file that is most likely a read-only file, like an executable or media file, and the user decided that such files should go to a different kind of storage, should go to a different kind of tier, this is the place where we can determine and apply all of that high-level file system kind of policies and permissions. And then the data is sent, in this case, to two nodes on the right. The choice of where we send the data to can be chosen per I/O, greedily, locally, according to the load that specific node is seeing from the different nodes, meaning that if it's getting better performance from some nodes, it can choose to write there, and can take into consideration load and latency. It can also take into consideration, when it chooses where to write the I/O, the heatness of this I/O. So if we see it's coming from a file that is most likely going to have an overwrite, we might send this I/O to a higher endurance SSD, while if it's coming from a file that we've seen that it's only sequential write, we might send it to a lower endurance SSD.
So there's no particular object ID to physical storage mapping?
No.
It's all dynamic?
Yes. So basically the way it works is that each SSD has some address space that you can, logical object kind of address space, you can address it. And then by choosing the OID of the data, you're basically deciding on which SSD it's going to persist. And this choice occurs at the entry point.
So the OID is actually hashed to determine what locations to go to?
Yes,
So,
yes, but it can change over time.
Yeah.
yes.
So I'm having trouble with the data and metadata paths being separated because it looks, unless I'm reading that diagram wrong.
We haven't gotten into the metadata yet.
Okay,
This
because
is
the
just
way
data.
the way it's drawn, it looks like that is data moving through the metadata.
So no,
path.
so it's just, okay, so it's drawn correctly. The data is just going to the data
Should
level.
be drawn around it, you're saying, around
Yeah,
the blue?
it doesn't go
Except
through
that's
in
not
any
the way it's drawn.
sense, except for on the image.
Got it.
Okay, and this is the metadata path, which does go through the blue aspect. In this case, the owner is co-located with the accessor, with the protocols there. It doesn't have to be that way. In case where you have multiple clients accessing the same file, it can go across nodes. And this is where we get all of the kind of nice scaling features of our metadata. So we have the dynamicity of ownership, which means that the ownership can move to be co-located with the accessor. This, for NFS operations, can reduce a lot of chatter, especially in this HCI mode, where because the owner is the only one who's allowed to write to the file, we know that any non-mutating operation that enters into this node, that node can respond to without leaving to the network. So in the case of HCI, this dynamic ownership allows us to respond to read-only operations without even leaving to the network. Okay, so we
Read
can,
only metadata operation.
yeah, read-only metadata operations, yeah. So for example, get attribute, which is a big portion of what runs on NFS, we just respond to it locally. So that's one advantage. And then the fine-grained aspect means that we can do this at a level of a file or directory. So it's not as if a bunch of files are hashed into a single bucket and this whole bucket moves around. Each file can move, the ownership of each file can move according to its requirements. And the reasons or the things that can cause ownership to move are either failures. So if this node fails, someone else needs to be the owner of the files it was owning. Access pattern. So this can happen just because of a vMotion. So when this node had a VMDK, it was accessing it through here, the owner would be here. We moved the VM here. Now it's accessing the VMDK through a different node. We'll move the ownership to that node. And because of kind of workloads of a workflow where one machine, one client is creating the file and then another machine is consuming that file. Okay, so the owner creates, is actually responsible for changing or updating the file mapping, saying in the right entry, I want to point to this OID. And this is encapsulated as journal entries, which are depicted here as purple hexagons. And they are sent to the same place where the data was sent to. So this happens by the protocol layer tells the owner where it has chosen to send the data, and then the owner will send the journal entries to the same place. Then these journal entries, together with the data, are persisted. Now, because our data is compressed, so even if a 4K block is compressed to 3.5K, we have enough room in that, what's left, to put the journal entries inside that, and then write that as a single IO. So this improves the wear or improves the endurance of devices, because instead of having two IOs, one for the data and one for the metadata, we can have one IO for both of them. And I remind you, we do not have NVRAM. Okay, so many systems do all of the metadata in NVRAM, and then they pour it down to SSD in a very long-term fashion. We don't assume NVRAM, so in a system like that, we would have to have two writes, and this is a technique we're using in order to have a single write, even though we're still consistent, power failures resistant.
So when a file open comes in, how do you know which owner of all the 1,000 nodes that owns that
That's a
file?
great
Good
question.
yeah.
So we have a service, which I'm going to talk about later, but I'm going to answer a question, which we call ORC, the Ownership Repository Coordinator, which is in charge of tracking who is the owner of what. When you access a file for the first time, you go and ask that service who's the owner of what, and it's also responsible for the recovery. So when a node fails, it knows what files that node was owning. It marks those files as requiring recovery. But I'm going to talk all about that in more detail.
Just on this slide, is it possible for an object to have multiple owners, have an object reside on multiple nodes for parallel access?
So a file can, You asked two different, I think you asked two different things.
For a piece of data at the data layer,
Yes.
for it to reside on multiple nodes, the same object copies on multiple nodes so that you have locality. If, say, you were doing an HPC type of a load where you have multiple nodes accessing the same data.
Yes, we're using N-way replication, so our way, in any case, it resides on multiple nodes. I'm not showing here what the read path does, but the read path can choose, because we have a 2 or 3-way replication, you can choose from which copy you want to read it, and you will choose according to the load you've seen from previous operations, and if that read is taking too long, you can go and read the other copy.
No, I'm talking about reads only.
So is
Yes.
it,
So for reads only, if you have a failure, I mean a device failure or a node that is serving, you would not notice it at all.
I'm talking about like a Hadoop workload, right?
Yeah.
You want to have 100 servers chunking the same data, but if it's all accessing on one node, you got a lot of that into node.
Yeah,
You know,
and I didn't mention it here, but we put every half mega of the file, it's spread evenly. So if you're accessing many nodes accessing the same file, but across many address space areas of that file, they will not even share the same SSDs necessarily.
is the directory metadata and the file metadata always resident in each node?
No. No. They are resident in the owner of that file or directory, only there. And if no one is accessing it, it can be evicted, as long as it went through the process of checkpointing, which I'm going to talk about in a minute. It can be evicted from memory. So only the actual working set needs to be in of the owner. Or you can look at it. The working set of the cluster will be in memory. Each one will be in a different owner. Now, this is at this point is the place where we can do what we call hiccup support or speculative write, which is basically means if we chose a node to write to and we chose incorrectly, that node decided to fail after we chose to write there, or maybe because it's just slow. So we can actually, because of this mechanism that allows us to do a fairly simple connection between the data and metadata, we can cancel this I/O and choose again where to write to. And again, the second choice can be according to the greedy current local locations that the node is seeing. And then again, we act the user only after the data is persisted.
And the data persistence here is at an SSD.
Yes.
Not necessarily in the memory of a server, but in the SSD.
No, it has to reach an SSD. You're 100% correct. Okay, and then in the background, we do a few operations. So one of them is checkpointing, which basically takes the metadata objects that have been changed and persists them as a whole to wherever they're supposed to be. Their address says they're persisted. As part of that, or following that, we can clean the log entries from the distributed log that refer to those specific objects. And then another thing that happens after we acknowledge the user is the dedupe part. We check if the dedupe is successful, and if it does, we point to the right location.
And the dedupe is at an object layer, or it's 4K?
It occurs at a 4K layer.
A compressed 4K.
Yes, but the hash is before the compression. So, but it points to whatever that object it is. If it's compressed or not, it doesn't matter. When you retrieve it, you see if it's compressed, then you decompress it.
And the hashing is done at the protocol level or at the
Yes, before at the entry, before sending any of the data.
And the hash is persisted throughout. The hash is persisted throughout the process and is checked on readback and stuff
Yes,
like that.
yes, yes.